Now, you've probably already figured out that the technology in question is the written word. In this lecture, you'll learn that even though our brains are not specifically designed for this technology at birth, prolonged and explicit exposure to it can repurpose parts of the brain intended for other things. And in the end, these cobbled together parts combine to create a neural network that eventually becomes dedicated to reading and writing in our mature brains. But first things first, is writing really a technology? I mean, it's obvious that airplanes and computers and clocks are technology, but writing? Well, why not writing? Writing is an external tool created by humans to solve a specific problem. Isn't that what a technology is? The problem to be solved is how to record what's in our heads and preserve it across space and over time. Speech is local and fleeting, but writing travels and lives on. This technology has revolutionized how humans communicate with one another. Never before could people from the past or from distant lands articulate their thoughts with such clarity and precision and then share them with so many other people. That changed everything. Most scholars trace the invention of writing independently back to at least two different civilizations: Mesopotamia and Egypt. The Sumerians of Mesopotamia are often credited with being the first writers. This is based on intact archaeological evidence of symbols inscribed into clay tablets dating back to about 3400 BC. And here's something to give you a sense of just how relatively recent that is. Some of the earliest and best preserved examples of these tablets are inscribed with written records of beer rations for Sumerian workers. To appreciate just how recent writing is, here's a nice analogy from the linguist John McWhorter. If humanity has existed for 24 hours, writing came about at 11:07 p.m. That's pretty close to midnight. For the first 5 millennia, writing was restricted to only a minority of individuals, elite individuals scattered around the world. It wasn't until Gutenberg's invention of movable type in the printing press in 1439 that the written word started to get much more accessible to the masses. But that's actually nothing compared to what's happened with literacy in the last 70 years. Data from UNESCO shows that in 1950, the world literacy rate was 56%. But in 2016, it was up to 86%. That's incredible progress over a relatively short period of time. And the quantity of writing per individual has gone way up. Between the internet, social media, and texting, people are reading and writing more than ever. And texting has given birth to an even newer form of writing. In 2015, the Oxford Dictionary named the emoji depicting a face with tears of joy as its word of the year. Before our very eyes, people are getting quite skilled with this evolving form of communication. Ever heard of the Chinese artist Xu Bing? His 128-page novel, entitled Book from the Ground, was published in 2013 as the first original tale to be told entirely in emoji. Okay, let's back it up. Let's focus on good old-fashioned reading and writing. And let's talk about how this technology has rewired our brains. Do you remember when we discussed how the fusiform face area isn't really a face area per se, but more of an expertise area? That example showed how something that clearly looks like an innately specified brain structure is different. It's actually a product of general genetic mechanisms interacting with specific experience over development. Well, reading and writing tell the same story. There are two main parts of the story, and both of them take place in familiar brain regions. The first part of the story, coincidentally, involves the homologue to the fusiform face area. Here's what I mean by homologue. If you recall, the FFA is located in the fusiform gyrus, which spans the ventral part of the occipital and temporal lobes. It's a bilateral structure, which means it traverses both the left and right hemispheres. In the case of face processing, the FFA is right lateralized, which means that the right hemisphere does most of the work. This should make sense given what we know about the right hemisphere being more specialized for global and holistic processing. So what's going on in the corresponding hemisphere in the left side of the brain? Stanislas Dehaene has dubbed that region the visual word form area. And from its name, you can tell that it's specialized for processing written words. This should also make sense given what we know about the left hemisphere generally. It's specialized for sequential and componential processing. Let me just take a moment to clarify what is and what is not meant by these homologs being specialized for different things. Both hemispheres are still involved in processing faces and words. It's just that the two sides approach them differently. And because faces benefit from a more global and holistic approach, the right hemisphere does more of the work. And because written words benefit from a more sequential and componential approach, the left hemisphere does more of the work. By now, this sort of neural distribution of labor should be familiar to you. But here's an analogy to drive it home. Imagine a boxer facing two different opponents. One is known for speed, the other for power. The best boxers would use all their skills for both opponents, but they'd focus on a subset of those skills for one opponent and a different subset for the other. The visual brain does the same thing. Depending on the stimulus it's up against, it engages the whole visual system while emphasizing specific parts that are best suited for the job. That's why the FFA works harder for faces and the visual word form area works harder for words. Make sense? Okay, back to our story. In addition to the left lateralized visual word form area, the second part of the reading network also takes us to familiar territory, the ventral and dorsal route for language processing. When children are learning to read English, for example, they spend a lot of time trying to sound out the letters of words. We know this from brain damage and neuroimaging studies that this overt sounding out during reading, it activates phonological mechanisms running up and down the dorsal stream. And even after children stop overtly reading aloud, they continue to covertly simulate this production in the same region. So here's how the two parts of the network get established in adult brains. Bradley Schlager of Washington University and Bruce McCandless of Stanford explained that through massive repetition and neuroplasticity, this sounding out process gradually helps the ventral and dorsal streams of speech processing connect up with the visual word form area. Of course, other areas are getting involved, but even this simplified model makes the main point. The neural network becomes established at different times for different people, but nobody comes into the world with such a network. It's not innate, and it requires experience with written objects to shape it. In this way, our reading brain is truly a technological transformation. Now, even though this neural network for reading is not innate and must be built over time, that's not to say there are no genetic components. One big reason why we know that reading is partly genetic is dyslexia. Dyslexia is common and is thought to affect at least 3% of the world's population. It's a very specific disorder that appears unrelated to overall intelligence. The National Institute of Neurological Disorders and Stroke defined dyslexia as difficulty with phonological processing, spelling, and/or rapid visual verbal responding. Putting aside spelling, note the two familiar pieces, sounding out words and visually mapping letters to sounds. That's our reading network. The heritability of dyslexia is estimated to be around 60%. What this means is that in the entire population of readers, 60% of the variance in the phenotype of dyslexia, in the behavioral manifestations of dyslexia, 60% of that can be explained by variation in genes across individuals. Let's use a more concrete example to try to understand this better. In industrialized countries, physical height is about 80% heritable. What that means is that only 20% of the variability in height is caused by variability in things other than genes, like the environment. Does this mean that the environment has minimal impact on height? No, it doesn't. Here's why. Because nutritious food is relatively plentiful in industrialized countries, there's not much variation in nutrition levels to begin with. It's pretty constant across people. In that way, the environmental stability helps the genes to fully express themselves. But let's say there's a global climate disaster and there's a major food shortage lasting for decades. And suppose that only relatively wealthy people could afford to eat nutritious foods. In this dark scenario, the heritability of height would go way down because there'd be much more variation in access to healthy food than there was before. Sadly, this is actually a reality in the world today. It's why the heritability of height is lower in some less fortunate countries that have highly variable access to food. What this means is that the genes for height across countries are probably more similar than we think. But because the food environment is so uneven, the genes can't live up to their potential everywhere. So, assuming a relatively stable and shared environment, you can see a strong genetic contribution to things like height and dyslexia. But what does that really mean, strong genetic contribution? Does it mean that there are specific gene networks in place that are adapted specifically for reading? Again, not quite. By now, you should know that for complex behaviors like dyslexia, genetic mechanisms are almost always designed for more general purpose functions. Let's come back to height. Suppose we discovered that being good at basketball was 80% heritable. Would you want to conclude that there are genes specifically designed for playing basketball? Of course not. Just like we don't have specific genes for making arrows, we don't have specific genes designed for complex things like basketball. Now, there are genes for more basic things like height or hand-eye coordination or muscle mass, and these things are definitely heritable to some extent. But they're not evolutionarily designed for basketball, they simply get co-opted for it. This is how we think dyslexia works too. There are genes for motor control and visual processing abilities, and genes for linking up those two systems. When confronted with the technology of the written word, the brain does its best to wire up the reading system. But in the case of dyslexia, there's some genetic malfunction with parts of that network. But again, this doesn't mean there are genes for dyslexia, just genes that get co-opted for the system. Most of the dyslexia gene candidates are involved in prenatal cell neural migration. We've talked about that. That's where there are genetic plans for what cells go to which places in the brain. This means that signs of the disorder should be identifiable at birth. I was lucky enough to be part of some research exploring those early precursors